Now, chapter 7, techniques of integration. Okay. Integration is not as straightforward as differentiation. Okay. In general, it requires a more elaborate effort. Okay. If we know the is antiderivative, then we can use fundamental theorem of calculus to do find the definite integral or indefinite integral. Okay. But there are some basic formulas that we can easily refer when we need. Here are list of the formulas. Yeah, you know this. We have learned this, and the antiderivative of sine is minus cosine, antiderivative of cosine is sine, and derivative of tangent is secant square, and antiderivative of cosecant square is minus cotangent x, and integral of tangent x is ln of absolute value of secant x, etc., etc. And integral of 1 over x square plus a square is 1 over a times arctangent of x over a, and there are the list of it. Yeah, I may give a number 1 and number 2 on those two, which we're going to use it in examples in section 7.1. And there are cases like this. We have a different integrals when this n is 1 or n is not 1, like this. So the integral may have a different form for the different index, like this. Okay, so there are, so this, you may have to see some of this, and some of the list may be new to you. But this is the theory. Indefinite integral for more complicated functions are generally more difficult to find. Okay. In this case, we may need to use substitution rules that we have learned. There are other sophisticated integration techniques which reduce complicated integration problem to more easily computable one, as in the list above. The one that you have seen in the first page is those are the example of the integration which is relatively easy. In this chapter, we will study some of the integration technique and integration by parts which can be applied to broad range of functions. We discussed two additional techniques, one for trigonometric function and the other for rational functions. We also discussed some approximation techniques for computation of definite integrals, and extended the definition of the definite integral to include integrals over infinite intervals. Okay. I may introduce you a single cell that we have developed. Here. This is for example, this is one example that you see. If we have a function like this, then this is the first derivative. This is the original function of the polynomial with degree c, and this is a graph of the first derivative of it, and this is the and And if you move, see, then the graph changes. Yeah, I think we can. If we move it, then that it gives us a new graph. And we can find the animations. Okay, this first graph gives us the original graph, blue one, and the second graph, red one, is the graph of the second derivative, first derivative, and the third graph, the purple one, is the second derivative, the graph of the second derivative, the original function of this. We can give very many different functions like this. Okay. Like this. If we can replace the function like this, then we will have what? E to the x is minus e to the x minus e to the x e to the x minus a, something like this. Then there are we're gonna so here, as you see, if we see the different functions like this, then if you have these three all together, then you can easily think about the antiderivative of the functions from here, if you can draw it. Okay. So now what you're gonna see is the reverse. Okay. How we can find the antiderivative? We were able to find the derivative without much difficulty, so we were able to draw the graph like this. Okay. Finding the antiderivative of the general functions like this. The first section, 7.1, is the integration by parts. 부분적분. You have studied those already in your high school years. Okay, because we know the product rule. The derivative of these functions are the derivative of this fg is f times g prime plus g times f prime. From there, if we do take an integration on both sides, then the left hand side will be f times g, and then the right hand side can be written in this way. So if we move one side to the other, then we have this formula like this. If we simplify it by substitute f of x as u and g of x as v, then that can be written in this way. I call it as equation number 4. Integral u dv is equal to uv minus integral v du. So when you integrate the function like this, then if you replace, if you let one as a u and the other as a dv, then you can easily use the integration by parts, like you see. If f of x is, let x equal to f of x, and g prime of x is equal to e to the 2x, then f prime of x is equal to 1, and g of x is equal to 1 over 2 times e to the 2x. So we will have this one as this times this minus this times this here, which will give us this. What is the technique to choose the proper axis here? So the technique is, if we choose this one as f of x or u, then the derivative of this will be simplified like this. The x goes to 1. x squared goes to 2x, and 2x goes to 2, like this. So it will be getting simpler and simpler. So that's the technique here. But if we choose differently, then as you see, if you choose u as a e to the 2x and dv as x dx, then du is this and v is this. So this integration can be written in this way. But as you see, in order to find the antiderivative of this one, you should be able to find the antiderivative of this one. But this integration is more complicated than the original one. So this is not a smart choice of u and v. Okay? So when you choose it, choose a simpler one as a u, the one which will be simplified by after taking a first derivative. They choose that one as one. Okay. So if we choose it differently, then it may getting more complicated than the original one. That is why we need to make appropriate choice of u and v. In particular, if g prime of x is equal to 1, then g of x is equal to x, does we have this goes to this? It's getting more complicated like this. Okay. Okay. First example, find the integral ln of x dx. Let u is equal to ln of x, then dv is equal to dx. So du is equal to 1 of x dx, and v is equal to x. So by the integration by parts, this goes to be x times ln of x minus x plus c. If we do it, I can show you in here. Then the integral of this one, that integral of ln of x with respect to x is this one, and the graph of the function is like this. So that the integration part works, and it's we could check it is right. And for the third example shows another case. When we are trying to find the integral of square root of x squared plus a dx, when a is positive, then we do use the integration by parts. Choose, let u be the square root of x squared plus a, and dv is equal to dx. Then you can find du like this, and v is equal to x. Then this I can be written in this way, and then this then this integration, this part of the integration can be integrated by the integration part once again to have this. From here we can solve. This is number one here. Okay. So in this case, after you've done the first integration, it was not done yet. So try to the second integration for the part of the first integration process. Then you found the I and the functions here without integration. So since you found the another I here, that you can replace it in here. So you do replace it in the earlier equation to have 2I is equal to the function of the right hand side like this, which gives us I is equal to 1/2 times the x times square root of x squared plus a times the ln of x plus the square root of x squared plus a plus constant. And this these integrations also do with a very simple command of the integration give us this answers like, oh, this is different. This is different. Okay, as here you have the unknown number a here, but if you replace the a as 9, then you can find the integral of hyperbolic arc sine of this value. That you can get it from here after you substitute the a as 9s. And that's the one, yeah, that's the one. The sage lines that to compute those. And if you make a slide bar on A's, then you can find the many of the different integrals for the different values of A's. Okay, next example 4. Evaluate this integral. Okay, here to do the integration, what kind of substitution will be proper? In this case, if you choose u as x square, then du will be 2x dx, and then the dv will the last of the integrations. And from here, you can find the v as this. Then we do use the integration by parts to have minus x square times square root of 1 minus x square, etc., which can be done in here. Okay, this is what you see in here. This is, so this, as you see here, yeah, this agree with the 1 minus x square to the 3 over 2 power, etc. So you can do the computations, integration by parts, but when you do the same computation and over again for the similar ones, then you can do it after you set up one code, then change the functions, because you already know the process. For this part, you let u is equal to x and dv as cosine x dx. Then it naturally gives you the very easy integration, because this x will goes to the constant 1, and that will makes you the second part getting simpler. There's integral e to the ax, like I put it here, like this. Okay, you can see, yeah, you can see the integral. What we did was right to find it. Okay, anyway. And evaluate e to the ax cosine bx dx. Okay, here you let u be the cosine bx and dv is equal to e to the x dx. Then du is like this, and v is equal to e to the ax over a. Then use the integration by parts to obtain this. What's interesting here is after one process of the integration by parts, you have a very similar integration, but with the sin x instead of cosine x. So you started with the integration with cosine, and now you have to deal with this integration with sine. Then using the integration by parts to evaluate this one, that will give you back to the integration of the function involving the cosine. Then you can mix up those two to substitute this into the equation above. Then we get the given the original integration can be written as this, which leads to the following equations. That can be done. With the sage. Yeah. So I made a general tool for that as well. I will show it at the end of this section. Next, using the fundamental theorem of calculus and integration by parts, the definite integral can be evaluated as follows. So if you have an integration by like this, indefinite integral like this, then all you have to do is just substitute a and b here and a and b here. In particular, the following is a special case of the above. Integral a to the b f of dx is this minus this. So that's the special case. So, Evaluate integral from a to 1 x times arctangent x dx. In this case, let u be the arctangent x and dv is equal to x dx. Then you know du is equal to dx over 1 plus x squared and v is equal to 1 over 2x squared. So, the integral from 0, 1 to x arctangent x dx can be written in this way with the integration by parts. Then, after substitute, you have this. Then you have to integrate the second part in the earlier process to have 1 minus pi over 4, which finally gives us the integration from 0 to 1 x times arctangent x dx as pi over 4 minus 1 over 2. Okay, so that's another example of the integration by parts. Integration secant x dx can be written in this way. You must have seen this. Now we do it once again. In this case, multiply secant x tangent x on numerator and denominator like this. And then substitute this secant x tangent x as u. Then du can be written in this way. And substitute it. In the original one. Then this can be written in this way, which is a simple integration of 1 over u with respect to u, which is ln of u. So u was defined in this way, so we should have this after substitute back. Okay. Next is a class example. Integrate cube of secant x dx. Okay. Let's define f as a secant x cube and integrate f with respect to x, which gives us this, which can be done in here. Also, this can be also done here, as you see. Can in secant x can be done secant x cube. Then this is the answer that you are watching it. Minus 1/2 times sin x over sin x squared minus 1 . This integration can be done in this way. Substitute u is equal to secant x, then dv is equal and dv as a secant square x dx. Then du is a secant x tangent x, and v is a tangent x. And using integration by parts, which gives us this and this, and substitute this tangent square x as secant square x minus 1. And then simplify it and use the integration of secant x dx as this, which we introduced up here. And now you have an equation which can be solved for integral secant cube x dx, which gives us 1/2 of this as the answer for the integration of cube of secant x dx. Evaluate the integral using integration by parts. Okay, you do this integration by parts. Actually, this is the code for doing integration to the integration by parts. Okay, what I did was let's define u as xv as log x minus 1, and v of x is a derivative of this big one, and capital U as an integral of little u with respect to x. Then I1 was the formula for the fit of it by integration by parts, and I2 is the integral of u plus little u plus big U. And then if you find I1 and I2, then you know what I did? This is the integration which was done by integration by parts, and this is just the sage comment to the integrals. So I found the I1 and I2, and I checked it whether they are same or not. And as you see, it is true. So this integration by parts really works, and so you don't have to write this long code. So you can do the same thing with a simple code like this. Okay, that's what I did, and answer was here. Okay, so now you have reviewed the integration by parts, and also you have seen some the completed integration which can be dealt with the techniques of integration by parts, and also the answers are same. The obtained answers are same whether by doing by hand or by the sage. And you may have interest of the early years of Korean modern mathematics. You may have interest on Homer Herbert and the Choi Kyu-dong, who was who had produced the math major student for the first time in Korea in 1915 at Jungdong School. Okay, exercise in section 7.1, integration by parts. For this case, you can do just you do the integration by parts, like you see, and you have some sage code for the integration of this function with respect to x, which gives you the same answers. And I have given the answers for all the problems here. Some are done by hand using the techniques of integration by parts, and some done by the sage cells. So you will be able to familiar with the computation of the integrations that you can often see from the many different books. Okay, so I think that's the end of this section 7.1. Reduction formulas. Okay, I think that's it. Any questions for section 7.1? Now we will continue the section 7.2, trigonometric integrals.